In this video, we are going to be speaking about reinforcement learning. We have been speaking about the history of deep learning, or maybe what would be more appropriate, the development of deep learning since 2015, 2016, until now that we are recording these videos in 2023. Perhaps one of the things leading to the widespread success of deep learning nowadays and its ubiquitous presence in our mass media and also in our research circles is that some ideas that had been defined before but were never, I would say, properly realized or were never deemed to work very effectively, now suddenly with deep learning have had a jump, have had an increase in this effectiveness. And one of these ideas is reinforcement learning. This is very far from a new idea too. Reinforcement learning can be traced back to those kind of psychological experiments or even animal behavioral experiments where some attitude is rewarded or punished in order to achieve one certain development. For example, an animal is given food if it can navigate a maze properly, and the hope is that by rewarding that behavior, the animal will actually learn to navigate the maze, to solve the task at hand by this combination of reward and maybe even punishment, depending on the action that the animal does. That, let's say, general idea, perhaps not the most ethical thing to do to animals now that I come to think of it, was also adopted in computer science in different areas, for example, games, but also areas such as industrial control settings, where we have a very narrowly defined scenario with very clear rules, and in those systems we can more easily establish this set of rewards and punishments or discouragements for algorithms doing one thing or doing another thing, or following one path or following another path. As I was saying before, from 2017, Google DeepMind again introduced AlphaGo Zero. We have spoken before how this same company achieved one of the major breakthroughs in artificial intelligence by actually solving the game of Go by using basically Monte Carlo tree searching and an evaluation function that was learned, that was trained based on image analysis. This same company decided to attack the same problem, the game of Go, from a completely different perspective, from the perspective of reinforcement learning, and design a program that was not given any human knowledge in the form of the many examples of games needed, for example, by the original AlphaGo to be trained to develop its evaluation functions for when a board was in a winning position or in a losing position. This new version, this AlpaGo Zero version, used only the rules of the game and absolutely no other human knowledge. So this software was designed only including the rules of the game, and this software used reinforcement learning, where it played against itself and it tried to achieve increasingly better performance by realizing in what strategies it found more victories and in what strategies it ended up in defeat, and rewarding those that ended in victories and forgetting about the ones that ended in defeats. With this, strategy, with these ideas, AlpaGo Zero originally managed to achieve a superhuman level of play in, first of all, Go, but then it was also adapted to play chess and shogi. And this was originally published in Archive, which is a whole other thing that we could speak about, but I will not get into today. But what ended up being published in Nature after polishing some things under the title Mastering the Game of Go Without Human Knowledge. And if you're interested in this subject, I highly recommend giving a look to, let's see if I can find it. Yes, this AlpaZero Wikipedia page that contains lots and lots of material, and here there are also references to the papers and DeepMind's all own page on the subject. I think this is a very good overview. But what I wanted to talk about today was that AlpaZero, in this very nice animation done by the people of DeepMind, started playing against itself and trying to realize when it was achieving something and when it wasn't, using this reinforcement learning idea. And in 3 days, it managed to surpass the abilities of the original AlpaGo, the one that was able to beat human being in a huge deep learning milestone. In 21 days, it reached the super improved version of that first software and could beat basically most human users. And in 40 days, AlpaGo Zero, this reinforcement learning version, basically arguably became the best player in the world and achieved maximum rating in the game of Go. As I mentioned before, this strategy of playing against itself and exploring, using the power of this huge deep learning network, exploring many possibilities, and using these computational capabilities of GPU, graphic boards. This same strategy was used for other games, like for example chess and shogi, and if my memory doesn't fail now, also for things like StarCraft and maybe even Atari games, other games that had been scenario for this kind of reinforcement learning types of software before. AlpaZero achieved amazing results in these scenarios too. For example, in chess, in 9 hours, AlpaZero was able to beat what was arguably then the best chess engine available, called Stockfish. Stockfish is, very broadly speaking, an evolution of Deep Blue. It's an algorithm that uses an heuristic to evaluate the positions of the board, so very human thought rules that evaluate how good exactly one particular configuration of the chessboard is, and uses min-max search, as Deep Blue did, to decide what is the best move that it can try when compared to the other moves that the opponent can do. AlpaZero trained for 9 hours and was able to beat this very good engine. AlpaZero was also trained at Shogi and managed to beat the best shogi engine, called Elmo, 90 times out of 100. There was some controversy about this, whether or not the computer configuration was right for Stockfish and Elmo and then AlpaZero or not, and the whole thing was repeated. The final results, AlpaZero and Stockfish played 1,000 games, and AlpaZero won 155, lost 6, and the rest were draws. So AlpaZero showed a very huge superiority over this until then computer chess champion. There were some variations of the contest between AlpaZero and Stockfish. The people at Stockfish, I remember one very public declaration saying that could not be possible, that AlpaZero must have been using some supercomputer hidden somewhere, because they were so utterly destroyed in this contest and they couldn't understand why. They were thinking that AlpaZero was able to compute many more positions every minute because they were in this min-max mindset, where basically the more boards that you can visualize and compute and process, the better you are. The point here was probably that AlpaZero was very likely not looking at so many boards at each moment, but because it had had all of this time playing against itself, it was probably better at pruning the search space and only having to look at a fraction of the boards that were possible at every moment. So even though the computation capabilities were not better than those of Stockfish, it was probably better at deciding what positions it should be looking at. I'm going to go out on a limb and say here that in that sense, AlpaZero acted in a slightly more intuitive way. Okay, intuitive as defined by, because it had trained a lot before playing against itself, it could bypass some of the boards that did not end up in a winning position and that were not obvious to Stockfish. Shogi, AlpaZero also won 98.2% of the games when playing black in Shogi, and 91.2% overall against computer that was better than any possible human ever could be. Reinforcement learning, very cool, but sometimes regarded as somewhat narrow because it's popular mostly in games. Another huge area of this is control theory and industrial processes, satellite positioning, these kind of things. And there are many more applications, especially emerging now. It's not a field that I'm confident we will see widely applied anytime soon because of this necessarily narrow definition. You need some very fixed and relatively simple rules, but it's a field that's gaining momentum, and deep learning has shown extensively that it can do very well in it. For example, here we have a couple more examples. Quantum compiling by deep reinforcement learning shows how reinforcement learning can help in the configuration of some quantum computing systems, if those ever get developed, and more. And here we have, for example, a blog that you can check that shows some other ideas, but this is a huge field with potentially many more applications.